Hello, my name is Zach Hollingsworth, and this is Group 20's NASA Psyche Mission Future Power Project. Here are all the presenters for today and who worked on the project. So, first, I'm going to start with a little background about our project. On October 13th, 2023, NASA Psyche mission launched a satellite into orbit to survey the asteroid 16 Psyche. The 16 Psyche asteroid represents a unique target for scientific exploration as the first predominantly metallic surface object NASA has sent a spacecraft to study. Located in the main asteroid belt between Mars and Jupiter, Psyche orbits in approximately 2.9 astronomical units from the sun, where solar irradiance is only 161 compared to 1,361 at Earth. While this mission is limited to orbital observations, future missions may involve asteroid surface exploration to expand scientific understanding and study of the asteroid. Which leads us to our mission. The objective of our project is to research and create a simulation environment for various solar energy technologies in order to design a power system capable of providing a constant, reliable power to all spacecraft functions for future Psyche missions. Here are our simulator objectives, which basically boil down to running various functions that account for all variables required to conduct an appropriate simulation of the electrical systems for a spacecraft. And here, we get a little bit deeper into the function of the program. The following page provides a high-level overview of the program's underlying functionality. This picture shows an electronic print of the system's components as well as all the variables required to run our simulation for each piece of technology. The core simulation engine is developed in JavaScript, enabling efficient client-side execution without reliance on server-side infrastructure. The technology database includes specifications for 32 distinct technologies organized across three primary categories: the concentrator, PV cell, and battery. Users can select technologies and define other relevant variables such as missions timeline, the loads on the spacecraft, and environmental conditions. Based on the active page the user is on, appropriate functions and modules are dynamically invoked to simulate scenarios and present results tailored to the selected inputs.
Garritson-White. This is our power project. Uh, so we worked on the 16 Psyche Power Simulator. It was a web-based engineering tool designed to help mission planners model, simulate, and compare power system configurations for NASA's 16 Psyche mission. Uh, 16 Psyche orbits the Sun at 2.9 astronomical units, roughly 3 times farther than Earth, which means the solar radiance is only about 12% of what we receive here. That makes power system design one of the most critical and challenging aspects of this mission. This simulator exists to make design process interactive, data-driven, and accessible. Over the course of this semester, we have changed the simulator from a basic technology selector into a fully featured mission engineering platform. So we began with core simulation engine, a physics-based model that accounts for solar concentrators, photovoltaic cells, uh, battery charge and discharge dynamics, and load profiles including instruments, heaters, and communications. The engine models a 48-hour mission window at 5-minute resolution, tracking power generation and battery state of charge at every step. From there, we expanded into 8 major feature areas. The multi-configuration comparison tool allows engineers to run multiple simulations and overlay their results side by side. The optimization engine uses a genetic algorithm to search across 32 available technologies and find configurations that minimize mass or cost while meeting power requirements. The advanced environmental modeling module adds radiation damage, micrometeorite impact probability, thermal cycling fatigue, and factors that become significant over a multi-year mission. We also built the mission timeline simulation covering all 5 mission phases from launch through extended science operations. A component sizing tool that works backwards from requirements to recommend array and battery sizes, and a cost-benefit analysis module with life cycle cost. Uh, modeling, and technology readiness level risk assessment. On the user side, we added 6 pre-configured presets along with uh, informational tooltips, a printable reference card PDF, and a power system architecture diagram. The results of the simulator is that it has passed 114 unit tests, a full PDF and Excel export capabilities, and complete technical report documenting the methodology and engineering decisions. From the previous page, you can see all the various things we have, and here are some of the key factors. We can export most things to a PDF, save configurations for the side display, we had 6 simulator options, a known functioning scenario, and we have downloadable and online viewable quick start and reference cards. Here we can see some of the basic information that's given when we run a simulation. And here we can see where we can compare them. This is the PDF that is output for the main system.
So for future work, obviously these are things that we've already accomplished, but the ultimate goal was to create a final repository and to finish product testing, stress test the system and simulator, in search of gremlins, make sure everything that we say it's going to do, it's going to execute, and obviously test the parameters to make sure that it's accomplishing what we say it's going to accomplish. And then obviously for the product or project demonstration finale, tailoring the simulator and the UI for the main audience and our customer. And then obviously providing a user guide. That way they could access it prior to using it. And then obviously wherever they are in the world, they can have access to it as well in a digital format and a physical format. And then lastly, obviously the big finale is the demonstration plan. So obviously demonstrate this virtually to our customer, and that way they can experience exactly what we've been working on for so long and enjoy it. And then after the demonstration, the goal in mind for future post this class is to have access to this anywhere in the world publicly. That way they could utilize it as a tool. And then conclusion. So obviously this product or project delivers an interactive power simulation solution and to explore a future energy solution for the NASA Psyche mission environment. We integrated solar concentrators, kind of photovoltaics technologies, energy storage options. The simulator enables meaningful side-by-side comparison across historical, current, and future technologies. Key features including configuration system parameters, saved configurations, export feature, in many different formats, and then enhance the usability for both technical and non-technical audiences, which is why we provided that user guide. The simulator supports education, concept exploration, and early phase mission analysis, and it helps bridge complex engineering concepts to the general public. Future work will obviously focus on the public deployment of this product where you're able to gain access to it. And then we're going to provide that demonstration to you live. And then we'll be open to questions. And then obviously you can enjoy this amazing project and what we're able to create.
Here we have the 16 Psyche Power System Simulator. You can see some basic information it gives about solar concentrators, photovoltaic cells, and battery systems. These are our various options. If you hover over, it'll give you a greater description of what they do or what they are looking at. The basic system architecture of our solar cells, and some overview information about Psyche. So going into the power simulator, you can see here we have configuration presets along the left-hand side for various missions. This last one is a known good mission. Also here, we also have the info tooltips, which gives it an insight into some of the information. We're going to select our optimal viable mission. This is your technology selector. So from here, you're going to pick what you want your system to look like using the solar concentrators, photovoltaic cells, battery systems. We've increased the accuracy of our models using NASA-validated accuracy models. And then the system parameters, which allows you to control the area of the concentrators, PV cells, battery capacity, base load, and duration and years in operation. All right, so we'll run the simulation. Comes up relatively quickly. From there, we can see average power, max power, minimum state of charge, and an end system, whether or not it's viable. In this instance, it is viable. Here we see the power generation profile. We see the peaks and troughs, and that has to do with when it's the sun is out and when it's not. You can see it goes up and down, showing us that it functions appropriately, keeping above the 15% SOC. Next, we're going to look at compare configurations. These are the known good one and then one of the other presets that is not viable, but we can click it. We can see very quick from at a glance that one is vastly preferable to the other, if only by the fact that this one's viable and this one is not. It's going to give you the same information you got from the previous page, except it's going to compare the various uh, parts. The overlay charts plot all selected configurations on the same axis, which makes it straightforward to compare how different technology choices, for example, silicon cell versus triple junction or a larger concentrator versus a larger battery, affect power generation and battery behavior across the same 48-hour window. For mission engineers, this kind of direct visual comparison is far more informative than reviewing individual simulation reports in isolation. It will support rapid trade-off analysis and helps identify which design decisions have the greatest impact on mission viability.
Next up is the optimization engine. I really enjoy this feature because as an engineer, you never want to have a single option. You always want to have multiple different scenarios and different things that you can pivot towards, especially when it comes to trade-offs. So as a program manager, for example, if you want to minimize mass, you can select that option. Or if cost is your initiative and you want to maximize that performance of the overall project based off minimizing the cost, you can select this one as well. Now keep in mind these are all presets. At any time, if you want to change it on your own manually, you can, but just you can just keep it as is. And you run the optimization. It's going to generate some results, best solution. Obviously, it's going to tell you if it's viable or not. And then provide an export feature for PDF or JSON. Once again, if you're an engineer and you want to build a white paper study, you can. And then if you want to kind of understand the evolution of progress in a graph, it'll provide that for you. So once again, trade-offs, extremely important. Options, extremely important. Pivoting as an engineer is extremely important. The next thing is mission timeline. This simulation tool is pretty nice, just because you can obviously change the battery capacity if you want to do with that, or change the actual solar cell type, and then the array, and you run that time simulation. Now, why this is important? Well, as an engineer, you can build something, a system, or some sort of tech, and it comes with a spec. That spec drives performance, and then you're able to gauge, okay, this is what this thing is able to do. The thing that it doesn't include is the time. So the life cycle of this product or the life cycle of this system. And at what point does the degradation start to happen with performance? And this will provide that for you, as you can see in the graph, and it can tell you, you end up having a failed mission at year 2 of the mission. Performance of the PV power started happening, as well as the battery capacity, but obviously it wasn't as extreme. So you can take that to consideration and kind of look ahead and see what's going to happen. And then it's going to give you the results. Essentially what you're seeing on graph, it's providing you the data points. It was able to launch in early operations, but then, with a deep space cruise, long duration, a 3-year mark, between 2 to 3 year, it started to have performance problems, and then it ultimately failed. And that's essentially it.
Okay, next we will look at component sizing. So the basics of component sizing is the user inputs mission requirements and the program automatically calculates the required sizing of power system components to meet the operational demands. So to take a look at this, let's change some of our specs. Make total mass higher and then randomly select our technologies. Now that all of our specs have been selected, we'll calculate. And what we get is our results. So the first section here is the required component sizes. These values define the physical scale of the system components needed to meet the user's energy demand. Next, we have the system matrix. These matrix describe the overall system performance and feasibility of the spacecraft we just created. And lastly, the sensitivity analysis. This section shows how much buffer or over design exists in the system. And then after that, you can either save the scenario or export it. And this gives you recommendations as you can tell that this random model we made, the configuration meets our requirements. Okay, going back. Okay, next we'll look at the cost benefit analysis. And in this section, it performs a comprehensive economic evaluation, including life cycle costs modeling, mass budget analysis, and technology readiness level risk assessment. So once again, if we add some random technologies, and just go ahead and make our areas a little bit bigger, we can see we get our results here on the right. The first one section is the life cycle costs. And this is the cost model, and it splits up the costs into four different components. The first one is development costs, which is technology dependent R&D expenses. Next is component costs, which is based on component quantities and complexity. Next is the testing costs, which is environmental and qualification testing. And lastly is operation costs, mission operations over the full lifetime of the mission. Next, we have a mass budget, which splits the overall mass into each one of the separate technologies. And lastly, here we get the technology readiness level assessment. So each technology in the database is assigned a TRL number from 1, which is basic research, to 9, which is flight proven. Higher TRL technologies have lower development risk, but may have lower performance than the emerging technologies. The cost model applies risk multipliers based on the TRL number, with a TRL of 3 to 5 technologies incurring a 2 to 3 time higher development cost than TRL 7 to 9 technologies that have been proven out in the past. Once again, you can export as a PDF or save the scenario.
My name is David Garritson, and I will start with the compare scenarios. The scenario comparison page is for side-by-side comparison of scenarios. Up to 4 scenarios can be saved for comparison. There are 4 available formats for data export. The multi-sheet Excel workbook with a separate tab for a summary, detailed data, cost breakdown, and mass budget. CSV format for spreadsheets, JSON format for machine data integration, and PDF format for presentations that include charts, metrics, and NASA ASU branding. The accuracy comparison dashboard page is for comparing the simplified calculations with the improved NASA data. The simple model uses ideal conditions with no degradations or losses. The NASA validated data takes into consideration a 0.3% average battery capacity loss per year, pointing losses of 0.5% to 5% based on spacecraft mission type, temperature effects on battery capacity and storage cells, and maximum power point tracking efficiency at 92% to 98% versus the simplified 95%. The user sets the parameters and the calculated values are displayed as key metrics data, graphs for the power generation and battery state of charge, and a list of accuracy improvements applied to the calculations. The help documentation page is a comprehensive help page using a professional card-based layout. It is accessible from the home page via a dedicated labeled button. It has 6 major sections. The quick start guide with 3-step tutorial in URL and PDF formats. The feature overview with descriptions of all simulator tools. The data export options with explanations of export formats. Tips and best practices with 5 recommendations for actions such as saving scenarios and checking system viability. Mission context defining different Psyche environment challenges. And data references and sources with hyperlinks to the references and data used for our project.